Hi, everyone. Welcome to the session. Oh.
This is Philip Judge. I will be attempting to moderate this session. We have people that really know what they're doing as well. One is Catherine Havilanis, who works at NCAR. She's going to lay out the instructions that you can see here. And also, of course, Andreea Pricopi is going to demonstrate some stuff for us. This is meant to be fun. Everybody should enjoy it.
Hopefully.
And we should expect things to go wrong sometimes. And if it doesn't, then we're very good. What time is it? We have 3 minutes before we're scheduled to start. Would any of you that have joined like to say who you are and where you're from and maybe what you're interested in? If not, that's fine. But if you do, you might want to try that.
Does anyone have any questions about the instructions if you wish to participate in the coding? Very good.
I see we have one person that I know a little bit on the list watching, and that's at least two of them actually. Janet Luman, welcome. I hope you're doing well. Janet is a well-known, very well-known leader in the areas we're studying here at this meeting, and I'm pleased to see you joining in. Alan Paraskiv is a postdoc working with me. Now's a good time to say who you are if you'd like to, quickly.
So can you explain, this is Janet, can you explain to us, Phil, how this is going to work for those of us who didn't do any homework ahead of time?
I will leave that to the other two who know much more about the details of this than I do.
Okay, thanks.
So as soon as we've got everyone ready, I will go through all of the details of how this is going to go. But if you want to follow along with my coding demonstration, you should have a Google account and you should be logged in, because we'll be using a Google product that requires you to have an account and be logged in. And you should also just have this link that's in the presentation. You probably received it by email. If not, I can drop it in the chat right now. And you just have to have that link accessed so we don't waste time with that. And from there on, I'll just explain all the steps as soon as I start the presentation, if that's okay with you.
I just opened it up. It's opened up immediately because I do have a Google account. So far, so good with me. And I see a basically what looks like a set of files listed, and
that's right.
let's see. Yeah.
So I'd say we give it maybe 3 or 4 more minutes, and then we can go ahead and get started.
Yeah. If I had planned better, I would have some coffee, but I ran out of coffee on Sunday night, and then we had to start again at 6. I had to get up at 6 a.m. on Monday morning and do some testing for this whole meeting at 7 a.m. And so it was just bad timing. But the dog served to wake me up. She wanted to go for a walk, so that was good.
That's good.
We have a nice collection of people here, actually, 13 already. The other thing I will mention to those of you taking part is if you have comments at all on how you think this meeting is going, you know, just, I will remind you of this on Thursday morning, but we'd be very interested in hearing what you think of this meeting. If it's been useful, what wasn't so useful, we'll let you know, but we're very, very open. This is kind of an experimental meeting, so it's important to get a little bit of understanding of how people felt it went.
Also, feel free to ask questions in the chat. You can also raise your hand using that reactions button, in which case we can call on you and you can ask your questions on camera.
Or just write in the chat if you're not comfortable with asking questions or camera. But please do ask questions if you have some.
When we do get started, Andreea, if you'd like to introduce yourself, that would be very nice after we get started, because I think some people will perhaps be surprised at your background. I've noticed several emails calling you doctor, which is very nice. My goodness, we're up to 17 people already. I had the privilege of talking to two of the poster participants, two women from India. They were in Mumbai last night. And I said, it looks a bit dark where you are. Where are you? They said, we're in Mumbai. I said, well, what's the time? They said, oh, it's okay. It's 1:41 a.m. So I felt kind of bad for those people at those longitudes.
It's quite late. All right, well, I'm going to stop sharing my screen, Andreea, if you would like to go ahead and share your screen.
Sure. I'm wondering if you're seeing my screen now.
Yes.
And is it a GitHub page?
It is.
All right, perfect. So, hi everyone. My name is Andreea Pricopi. I'm a fourth-year computer science student from Romania, and this workshop is inspired by my research for my diploma thesis. What we're going to do today is go together through the basics of a machine learning project, and the goal of today's meeting is for you to understand the basic steps of such a project and how useful and accessible some tools and concepts might be for other projects of your own. We're going to perform a binary classification on a set of artificial solar data, and I'm going to describe the task in more detail soon. But first, I would like to tell you how this is going to go. We'll basically look at some data, analyze it, pre-process it, try some basic algorithms, test their performance, see what we can improve, and basically do this all again, because this is how machine learning projects work. I have prepared a Jupyter notebook for you, and I'm suggesting you follow along with my demonstration. Initially, I thought about you having more coding to do. I thought about it as more of a hands-on experience, let's say. But in the meantime, I realized that maybe we should just look at the broader picture together. So please do not feel concerned if you don't understand the syntax. That is not what machine learning is all about. Just try to understand the concepts. We're going to use Python with a few libraries and packages. I've linked them at the end of my notebook. You have links to all of the stuff that we're using. You also have my email address there if you want to continue this discussion or if you want to ask more about this workshop or notebook. And please do not worry if there are any terms that you're not familiar with, because I will try to explain everything in enough detail for it to make sense, but hopefully not overwhelmingly. So let's get started with the setup. Do you have this same GitHub page open in your browser? You might have the light theme on, so that's no difference if you don't see a dark screen. You should basically just see these files here. There's a title that says Second Eddy Cross Disciplinary Symposium, parallel session. It has my name on it. And what we see here called end-to-end binary classification.IPyNB is the Jupyter notebook that I was talking about. For those of you who are not familiar with Jupyter Notebook, it's simply a type of document that allows you to have code and execute it inside it. And we're going to access this notebook today through Google Colab, which is a Google product that lets you edit and execute this kind of notebooks without you needing to install or download anything, which is very convenient for today. And I'm going to show you how to open this notebook that I have prepared in Google Colab. So please click on the end-to-end binary classification.IPyNB from IPython notebook and open it in a new tab. And something similar to what you see, hopefully see on my screen, will show up, which is the notebook. And in order to open it in Google Colab, you just need to go to where the URL is. So where the link is, click there. And right after the word GitHub, before the dot, you have to write to Colab. So to Colab, TOCOLAB. After the word GitHub and before the dot. And then simply press enter. And what you see here is the Jupyter Notebook in Google Colab. As I was saying, we're going to use Python with a couple of libraries and packages that you can see here. And as I've told you about already, they are linked at the end of this notebook. And you would normally install this on your machines. But in order not to waste time with that, I've written all the lines that you need to run in order to have all the prerequisites for this. And you're not going to install anything on your computer. They're simply going to be installed in this environment, in this Google Colab environment. This is basically a code cell. And in order to execute it, we can either press on this arrow button that looks like a play button in the left side corner of the cell, and it says run cell, or we can just click on the cell and then press Ctrl plus enter. We're going to do this immediately. I'm just telling you what's in the cells. So basically we're installing here some of this stuff that we're needing. Then we're importing some stuff, writing some configurations so that we have everything running the same way on all of your computers. And then there are some functions that I wrote. You do not have to worry about this. They're mostly used for displaying stuff nicely in a way you can better understand it. Do not worry about the code here. We can talk about it if you want to, but it's out of the scope of today's presentation. This is not what machine learning is about, as I was saying. So as I was saying, we can just execute each of this cell separately by pressing on this arrow button or pressing Ctrl plus enter, or we can just minimize the prerequisites by pressing on the arrow next to the title that says the prerequisites, and they will collapse. So the cells will be hidden. And if we press on this arrow right here next to the text that says 7 cells hidden, it will automatically execute all of the things that we need in order to get it up and running for everyone. So please press on the arrow that collapses the cells next to the title that says the prerequisites, and then press on the play or run button next to the text that says 7 cells hidden. It will probably ask you whether you trust this notebook and you want to run it, and hoping that you do. And if you do, I hope, please press run anyway. And right now, Google is doing everything that we need to have the notebooks running. And in the meantime, I'm going to introduce the task at hand today. Please tell me if any of you has any problems with the setup so far.
Everything's fine with me, and I'm the old guy on the meeting, so I'm not used to Python. I'm an old Fortran guy, so hopefully everybody else is doing okay. Please do speak if you want us to wait.
All right. So the problem today is the geo-effectiveness of coronal mass ejections. Coronal mass ejections are explosions from the sun's corona that look like this one right here, that you can see right here, that sometimes can hit Earth and disturb its magnetic field. And this effect is called a geomagnetic storm. I've also linked all these terms here. So if you click on these names and want to find out more, you have more information from people who know even more than I do about it. So sometimes these coronal mass ejections disturb the Earth's magnetic field, and that is called the geomagnetic storm. And the way we can know whether a geomagnetic storm occurred or not is by looking at a D index called the DST index. And what we'll be using for today's notebook is this value of -30 as an indicator of a geomagnetic storm. So if the DST index has a value less than or equal to -30, we can say that there was a geomagnetic storm, and hence that the coronal mass ejection, the explosion that you see right here, was geo-effective. And what we want to do today is basically predict whether a coronal mass ejection will be geo-effective, knowing only solar parameters that we have about this coronal mass ejection at the moment or close to the moment of its occurrence. We will therefore want to predict a value of 1 if we believe that the coronal mass ejection will be geo-effective, or a value of 0 otherwise. And since we want to predict 1 out of 2 possible values, the test that we're performing is called a binary classification. If we had more target values, more labels that we predicted, the task would be called a classification task. And if we wanted to predict a continuous value, like DST, if we try to predict that, then it would be called a regression task. But what we're doing today is binary classification. So we're going to try to predict 1 or 0 if we believe that the coronal mass ejection will produce a DST value lower than or equal to -30, or 0 otherwise. And now it's time for us to look at the data, because most probably this finished executing for everybody. And as I was saying, I have created an artificial data set that is based on the LASCO catalog, for those of you who are familiar with that. I have linked it here if you want to find out more information about that. Otherwise, the next few moments will give you all the information that you need in order to perform this task. What we're doing here is reading a CSV file from my GitHub using Pandas library, which is a Python library used for data analysis and pre-processing, in a variable called df from data frame, which is its data type. And it simply refers to a way of storing or keeping tabular data. which we have in a CSV. So we're going to execute this cell by pressing the Run Cell button. And now we have the information read in the variable df. And if we want to look at it, we're just going to press the next Run Cell button. And hopefully you can see a little sneak peek of a table. And what we see here is a number of solar parameters. They're called central position angle, angular width, linear speed, acceleration, mass, and kinetic energy. And we also have the DST index that we've talked about. And you have all of this linked here to the LASCO catalog. If you want to find out more about them, you've also have their measure units. I hope that's the correct term here. And this is basically all we need to know to go further. And now the first step, which is also the most important one, is pre-processing our data. And I'm saying that this is super important because with machine learning, the results are as good as the data you feed them. And computers usually only like numbers. So it is up to us, the humans, to ensure that we're only feeding numbers to the computer. And if you look at our data here in the sneak peek, you can probably see that we have some values that perhaps wouldn't be understandable by a computer. Like we have this NaN values that basically mean not a number, which must probably mean that these cells are empty. And we also have some dashes in the DST column, which is obviously not a number. And this probably means something that you would normally look at the source of your data for, some information about what this dash means. And since I am the source of this information, I'm telling you that this means there was no geomagnetic storm. So what we have to do now is basically look at this information automatically and see if what we observe so far can be understood from this as well. So these are just two instructions that give us some extra information on our data. And basically we can see the columns that we have here, and we can see how many non-empty columns we have. And we can see that out of this many entries, we have a missing value for angular width and very many missing values for these two columns. And we can also see that the DST value doesn't have a numeric type, which should not be the case. So what we're doing here, what we have to do now is get rid of these empty cells. And we have some options here, which one would be to try and fill them up. But since we're no solar experts, or I am no solar experts, and maybe some of you are not, we might not know what value would be reasonable and physically correct to put in these cells. So we most probably have to get rid of some stuff. And we could either remove the rows that contain missing values, but since there are so many missing values for these two columns, if we deleted all the rows that contain missing values, we'd lose a lot of information. We'd be left with less than 4,000 examples out of 15,000. So the other option that we have is to drop these columns altogether because they don't give us much info, which is what we're going to do now. By executing this cell, we're basically just saying drop these two columns with the name mass and kinetic energy. And so we're going to execute this cell. And if we go back and execute these two cells, this cell again, we can see that we no longer have those columns here, but we still have this missing value for the angular width. And since it's just one missing value, we could drop the row because we wouldn't lose much information, and it would be unreasonable for us to drop the entire column. So what we're doing here is basically dropping or deleting all the rows that have no information in them. And that's what we're going to do by executing this cell. And what we're left with is the problem of the DST. And so what we want to do, since I told you that the dash means there was no geomagnetic storm, is replace that value with 0, which is a reasonable thing to do given that any value greater than -30 means there is no geomagnetic storm, which is the information we actually want to introduce in our data set. And what we're doing basically is saying replace all the DST values with 0 if the current value is equal to dash, otherwise keep the current value. And so we're going to execute this cell. Moving forward with our task, the next thing that we want to do is introduce the thing that we're looking for, because now we don't have any other information regarding the label, the geoeffectiveness label, other than the DST, which is what we actually need. So what we're doing now is create a new column in our data set based on the DST value. And what we're saying is set this threshold to -30. And then in this new column, put 0 if the DST is greater than the threshold, and otherwise put 1, which means geoeffective, as we've already talked about. And then we're going to delete the DST column because we will no longer need it anymore. It will be redundant since all the information that will be in the new column. So we're going to execute this, this step now. Is everything clear so far?
Yeah, I think so. I had an error on, let's see, the first df.drop. It said remove, blah, blah, blah. I don't know, it's a traceback that I think is telling me there.
You might have clicked on it twice, and since the first time it removed the columns,
okay, yeah.
Cannot
Okay.
find these columns.
Yeah, and the other one's executed fine for me.
All right. Okay, so we'll be moving on with our task. And the next thing that we need to do is tell them what we know and what we want to predict. And this is what we're doing here. We're separating the inputs, which by convention are called X, from the output, which by convention is called Y. Just as in a mathematical function, this is what we know, and this is what we want to get, or this is what we're going to use as an output and train on. So by executing this, we'll get the value, all the columns that are not called geoeffective in X and the geoeffective column in Y. And in order to test that everything went smoothly for everyone, in the upper left corner, there's a cell that says code. There's a little plus sign, and if we click on that, there's a new cell that will appear. And if we write X and then execute, we can see that we have a table with all of the columns but the geoeffective one. And if we write Y and execute it, we can see that we have the values in the column called geoeffective. And what we're going to do now is more splitting. And for that, I want you to think of your school days, and I want you to think of a good teacher. Now, would a good teacher test you on the exact same exercise with the exact same data as they trained you on? Or would they use slightly different data, which is hopefully the answer, because otherwise the teacher couldn't tell whether you've just memorized or learned by heart the information they gave you or the data, rather than you being able to generalize and to perform well on unseen data. So what we're doing now is setting a part of our data apart. We're putting it aside. We're not going to touch it, just as you wouldn't cheat on a test by looking at the questions beforehand, to keep for testing our models. And we're going to use 20% of our data for that, which is a commonly used value. this is what's happening here, but I'm going to explain the code a bit because there's some interesting things that are happening. So we're basically saying, split the inputs into these two sets, split the outputs into these two sets by keeping the test size equal to 20% of our data. And then we're saying shuffle, which basically refers to randomly shuffling the data and then performing the split. And the reason we're doing so is similar to why we wouldn't pick the very first exercises in a book or the exercises that are the very bottom, because usually exercises are ordered by difficulty. So if we just, let's say, took the 20% data from the bottom for the test, we might get only the hard exercises. So what we're doing is basically shuffling the data and then doing the splits in order to have chance to get samples with various degrees of difficulty, let's say. And we also say stratify by Y, which is our output that is 0 or 1, if you remember this. And we're doing this because when we're shuffling, there's no guarantee that we will get both zeros and ones. We might only test on zeros, or we might only test on ones, which is not what we want to do. We want to get a realistic view of our performance. So we're ensuring that in the test set, we have the same kind of proportion of zeros and ones as in the original set. And there's one more line that says random state equals seed, which basically ensures that by attributing using this seed, which is this number right here, and we can execute this cells to be sure that we have this seed set. We're ensuring that each time we run this notebook, we get the same results, even if the shuffling is at random, and that everyone in this meeting is getting the same results. So we're going to execute the split now. Is everything clear so far? All right, no answer. I'll take that as a yes. Please feel free to intervene if not. And there's one more step that we need to do. And I want you to think of our good teacher again. And what a good teacher would do is they wouldn't simply train you once and then send you to the final test. In between, you would probably do some testing with no, let's say, punishment or reward whatsoever. Their scope would be simply to evaluate whether you've understand the data, whether you've trained well. And if not, you can go again, change something in the way that you're training, and then try again maybe. And only after you're sure that you can perform well and you're feeling satisfied with how you perform, you go and test yourself on the real test. So what we're doing now is splitting this set that is not the test set into two more sets, into the actual training sets, and a set that is called dev from development. And it basically will be basically used to improve our models. So we're going to train on this set only, then test ourselves on this dev set, see what we can improve, and then do it again. So let's execute this cell 2. And now we basically have 3 sets: the train set, the dev set, and the test set. And the test set is the only one that we're not going to look at all, but we can use the entire train dev to analyze the data, which is what we're going to do now. And here we're basically saying put temporarily the inputs and the outputs together so that we can look at this data as a whole. So let's run this cell, and we can see that we now have in this variable the entire train dev set. And what we have here is a tool called Pandas Profiling. And if we run this, we get a complete report. So please do execute it because it's going to take a couple of moments. We get a complete report of our data. It will include some statistics, some histograms, some valuable information that you might usually look in different places for. And what we have here basically compiles all this information for us. We're not going to spend too much time looking at everything that this Pandas profiling report has to offer. I will let you do this for yourself, but I will just give you a hint of what we can see. We can see the number of variables that we have of observation, the number of missing cells, and we can see that we did a good job by eliminating the empty cells. We can see how many numeric ones and how many categorical ones we have. Here we have the index, which is just the ID of the data set. We do not care about this, but here we have the first column in our data set, which is the central position angle. We can see how many distinct values there are, the minimum, the maximum, the number of zeros. We can see its mean. We can toggle details and see even more. We have some descriptive statistics here, like the sum of all the values, or whether this is monotonic. I do not know the English word, I'm sorry. We can look at a histogram, which shows us this distribution of the variables. We can look at what the common values are, and we can see that, for example, most of the values are 360 in this case. We can see at the extreme values, like the minimum 5 ones or the maximum 5 ones. And we have all this information for all of the columns. We can go through them. We have some interactions here, which is basically the equivalent of scatter plot, just a bit stylized. We have correlations already computed for us and graphically displayed. We can see that, for example, there's a high correlation between the angular width and the linear speed. We have some descriptions about the correlations. And I think that if we look at the overview and the warning, we can actually see some information about which column is correlated with each other. We also have a sample of some data. And let's look a tiny bit at our GeoEffective column. Let's look at the details. Yes, please.
So currently we're looking at the statistics of the input training set of data. Is that right?
Yeah.
Okay, so there's no actual regression done at this point or anything like that?
No.
I just wanted to make sure. I might have missed something, so please carry on. Thank you.
We're just looking at the data. We need to get a good grasp of data so that of the data we're working on, so that we can understand something from our machine learning results.
Okay.
And as I was saying, we can look at the categories that we have for our label and see their distribution. And now that we've seen something about our cells, it would be probably useful if we could see our entire data set. But having 5 features means that we have 5 dimensions, which might be pretty complicated for us humans to visualize. I don't know if it's just me, but I find it that bit complicated to see points in 5D on a 2D screen. And for those of you who, like me, cannot do this, there are techniques called dimension reduction techniques that basically can take your input of data containing as many dimensions as it has and translate it into fewer dimensions by basically embedding, encapsulating the essential information. It's obviously a simplified way, so you're losing some of the information, but the new variables that you're getting encapsulate the essence of your data. And what we're going to use today to get a 2D representation of our data is called UMAP, from Uniform Manifold Approximation and Projection. And it's based on some advanced maths that is out of the scope of today's workshop, but I've linked it at the end of this document for those of you who are curious about how this works. All that we have to do is write UMAP, assign this seed to be sure that we always get the same results, because there is some randomness somewhere in the background. We could specify the number of components that we want or the number of dimensions, but you can see that the default one it's written here that n_components equals 2, which means that the default value is 2. So if you're not specifying any number of components, it will give you a 2D representation of our data. And what we're doing is getting the 2D representation for our train dev inputs and the dev inputs only. So please execute the cell, as it will also take a bit. And the next thing that we're going to do is look at a plot of our data. We're going to have on the column X the first component that this UMap is giving us. And on the Y-axis, we're going to have the second component. We do not need to understand now how they were computed. We only need to get a better visual idea about how our data looks like, and especially how our columns, how our labels look compared to one another. So how the geo-effective data looks compared to the non-geo-effective data. And this information we're going to get by coloring the dots based on the Y value. So those that are 0 will get a color, and those that are 1 will get another one. My cell executed, I'm going to execute this one as well, which is just a function that will do this, and then execute the actual plot. And in a few moments, you can see a 2D version of our data. This is the entire train dev set, so the train and development set. We can see that we have many non-geo-effective samples, those that are colored in blue. We can click on this label right here that says color equals 0, and it will make the majority of the dots disappear. And now we can only see the geo-effective data. And if we look at the dev set, we can see that it kind of resembles the train dev set, which is what we wanted. It means that we have representative and meaningful data in the dev set that we're going to test on. And we'll basically move on now to the machine learning part, and we'll come back to this to see our predictions on this plot with different colors. And now that we're moving to the exciting part, I should let you know how a machine learns. And the whole magic that happens in the background for a machine to learn is basically it's trying to discover a function that best represents the relationship between our inputs, which are our solar features in X, and our output, which is Y, our label. And the way it does so, it's not by randomly trying different functions. Like it's not trying a linear function and then a polynomial one and then maybe a sinus. Based on the model that you're choosing to try, you're basically specifying the base function that you're going to try and find the parameters for. And the first thing we're going to do is apply a logistic regression, because before trying to work with a neural network, you should know how simpler models perform, because you might not need a neural network for simpler tasks. And the function behind the logistic regression is the one that we have right here. And in X, we have our features, and we're trying to find a weight for each of these features and a constant bias that would give us a Y value that is as close to the real one as possible. And this is what basically the machine is trying to do. It's trying different weights and different B values to try and find the ones that give you the lowest error. So the lowest difference between the target value and the one that is the result of this function. And I will show you a little view of how this is happening. I'm sorry if it's too fast. I've tried to give it a lower speed, but it doesn't seem to want, it seems that Google Colab, it's speeding it up anyway. We'd better wait until, yes, please.
this is W here really a matrix? Or is it a?
It's an array.
So is that a matrix multiplication of some kind?
This is
star?
our array of features, and this is our array of weights.
Okay, so is that a scalar product?
I
One,
think that is the word.
so that gives you one number plus B.
No,
each-
no. Okay, so no, it's not the scalar product. Yeah, it is a matrix like multiplication. We're basically
so-
multiplying each of this weight with each of these values with each of the samples that we have. So for a row of x's, we're basically multiplying each W corresponding to each x value, and then applying this bias. And oh yes, this gives us a single number, which is our target. I'm sorry.
Okay, so it's a scalar or dot product, an
Yes.
internal. Yeah. Okay, great. So and this
my
defines
bad.
what you, and this is a characteristic of this logistic regression model specifically, just to get, is that what this is called? This algorithm?
So the principle behind this, trying to discover the values that we need for the parameters of a function, is the principle behind all learners. So if you're going to try a neural network, you're just going to try and find more parameters for a more complicated function. But the principle of trying to find weights is the same. That's what's happening in the background.
Okay, so sorry for the stupid questions, but I've never.
No, it's all right. There's
no
no stupid question.
Thank you. Okay.
All right. So what we're doing here is waiting for this to start from the beginning. Let's see if we open it in a new tab. All right. So at first, we're just assigning some random values. We do not know what we're looking for each of this. And then we're trying to make a prediction. And then we're looking at the real value and see, oh, okay, we've predicted something way lower, so maybe we should increase our weights. And then we're trying again with bigger weights, and we make another prediction and compare it again and see that this time we should have predicted 0, which means, okay, maybe we should decrease some of our weights, which is what we're doing. And then we're doing this again and again until the difference between our predicted value and the real value is low enough for us. And this is what's basically happening. Is that clear for everyone? I sure hope so. So moving on, we're basically going to perform the logistic regression. And we're doing this by simply writing logistic regression. This is imported from the scikit-learn library, which has most of the machine learning things that you might need. And since there's this random initialization of the weights, we need to assign this seed to the random state to ensure that each and every time we start with the same weights. So we're going to execute this cell. And now we have a logistic regression model that we're going to train. And we're doing this by simply writing .fit and specifying the data that we're using to train our model, which is X-train, the input features, and Y-train, which is the output here that we're going to compare our results with, that it is going to compare its results with in the background. So by clicking on this execute button, we've just trained our model. And the next step is test it on the dev set, which is what we're doing by writing the name of our model .predict and using the input features for the dev set. And we're saving our predictions in here for future comparison with the real ones. So execute this cell with the prediction. And now we've already have our predictions. We can add a new cell and write dev.predictions. You do not have to do that if you do not want to. You just simply see that you have an array of predictions for each of the inputs in xdev. And by writing this line, basically accuracy underscore score of YDev, which are our real target values, and the name of our predictions, we will see the accuracy of our results. And it's 0.9909, which basically means 99.09% accurate, which is a great result, right? We're making a correct prediction 99 out of 100 cases. So let's look at the data, the original data colored by the original label in the dev set, and our predictions colored by the value of our predictions. So here we have the original data, and here we have our predictions. And we can see that we have no value of 1 predicted whatsoever. And we haven't predicted any geo-effective CME. And if we actually go back and look at the report, we could actually see that it actually told us that 99.1, which is probably an approximation of that 09 value of these geo-effective column values are zeros, which basically means that if we tried to predict it, the geo-effectiveness of a coronal mass ejections, and we only said 0, for this data, we would be 99.1% correct, which is a great value if correctness is what you're looking for. But our task is similar to weather forecasting. It's just solar weather forecasting. So let's try to look at it from a different angle and see if being correct 99% of the time is what we're looking for. Let's say, therefore, that we want to predict weather conditions, and we want to predict something so rare as snowing in a summer month in a climate that only has snow in December, January, and February. So it's highly unlikely that it will snow in July. But you as an authority should warn your citizen if this happens, right? And the cost of you not letting your citizens know that on a particular day in July, it might snow, and them being in shorts and t-shirts outside is probably higher. So the cost of this, of you not letting your citizens know this, is higher than you being wrong a couple times. So you basically telling your citizens it might snow twice this summer, which might sound absurd, but you are right in one of those cases, and your citizens were warned. So maybe a better way of looking at our data is through the number of true positives, which is the number of correctly identified geo-effective events, rather than your accuracy. And what we're doing now is look at the recall, which is this true positive rate, and the precision, which is the number of true positives out of all the positives predicted. And we can see that both values have 0, which is expected because we didn't predict any true positive. And this is because basically we have 99%, more than 99% of our data being not geo-effective. So what our model sees and trains feels like this. It's basically saying, okay, so this is what you're in class and this is what you're training on, and then you're spending an equal time doing this, and then, oh yeah, we're doing this, and then we're doing this again, and then we're doing this again. And when you test it, you're actually giving this that you've only spent a super limited amount of time in class to learn, that is way harder to understand, and you're getting your performance measured based on how well you know how to do this and not this, because apparently for the world this is more important, which is what we're saying, that we want to identify the geo-effective events because we care about them more rather than the ones that basically do not hit Earth. So in order to solve this, what we're going to do is say, take all of the time that you're spending on training on this and learning this and split it like this. You're going to spend the amount of time that you're using to learn this for simple task for this complicated task only. So let's say that this we would initially assign 2 minutes per each of this exercises, which is equivalent of a sample. This is a not geo-effective sample, and this is a geo-effective sample in our data set. And the time that we're spending is actually the importance of the sample in our data set. And so if we had 10 minutes, 2 for each, we're basically saying, no, do not spend 2 minutes on this. Instead, spend 2 plus 2 plus 2 plus 2 and spend 2 on this. So spend 8 on this and 2 on all 4 of the simple ones. Does that make sense? I will take it as a yes if nobody says a no. And in order to do so, what we're doing is basically just adding to this logistic regression this simple parameter besides the random seed that says class weight equals balanced. And it's balancing the effort that we're spending on training on all the examples. And then we're going to fit our data, make predictions again, and then evaluate our performance. If we run this cell, and this evaluate performance is a function that I wrote that prints all of these accuracy, this performance metrics and this confusion matrix. So what we can see now that we've assigned balanced weights is that, yes, our accuracy decreased, but we're correctly identifying 86.36 out of the geomagnetic storms. So in 86 of the cases, roughly, we are warning our citizens of snow in summer. Our true negative rate, so the numbers of times we're saying it won't be a geo-effective storm and it actually happens to do so, is 94%. And yes?
Question here. Actually, if you just go back to the predicted data, what are the blue dots and the red dots corresponding to? Can you explain that?
Yes, of course. So the blue dots are in this first plot, which is the plot of our original data. The blue dots are the dots that have a geo-effective label equal to 0, which means not geo-effective. And the red dots, let's make this disappear. The red dots are the samples that have a geo-effective label equal to 1, meaning they were geo-effective events. And in this one right here that for some reason I think zoomed in. Okay, these are our predictions. And since we only predicted values equal to 0, so we're saying we believe and we're pretty confident that there will be no geo-effective events. So these are our predictions and they're all non-geo-effective. Does this answer your question?
Yes, it does answer. Although when I'm running the code parallelly here, I'm seeing some of the red dots also in the predicted graph.
Okay, this is interesting. Do you have our seed equal to 42? There was a line that said seed equal to 42, and if you have random state equal seed assigned everywhere, we should all, theoretically speaking, have the same results. Did this happen to anybody else? Does anyone else have correctly predicted values in our first run? I can
No,
I see
wait,
there's some.
I got it wrong. I had checked the wrong graph actually. I was checking the
All right.
previous one. Yeah, so carry on. Yeah.
All right. Okay. So we have these results. We're basically having some false positives now. But these are the results that we got so far. And from now on, we'll be looking at how to improve these results. Let's look how many times does our model need to go over the data in order and make changes on the weights in order to achieve these results. And if we execute this line below our confusion matrix, which I haven't explained, but what's basically in here is the number of true negatives. So the number of correctly predicted as non-geo-effective. Then we have the number of false positives. So what we're predicting as geo-effective, but was in fact not geo-effective. We have the false negatives, which means the geomagnetic storms that we haven't identified. So geo-effective events that we haven't correctly identified. And the true positives, which is the geo-effective events that we have correctly identified. And after running the cell below, it says that it needed 43 iterations. So it went through the data 43 times in order to achieve these results. And the thing we're going to do next can improve, in some cases, our results, but it always decreases the time it needs, a model needs to achieve optimal results. And I'm going to show you a small graphical representation of why that happens. What we're going to do basically is scale our features. So basically assign to each of the value its value minus the mean of its column divided by the standard deviation of that column. There are other ways of scaling your data, like normalization, which is bringing your data to a range of from 1 to 0, or min-max scaling. But what we're going to use here is called standard scaling. And the reason this speeds up the computation is going to be graphically represented now. Can you see my paint window? Can someone confirm that you can see a paint window? All right. So let's think of our task as fitting these rectangles in this red rectangle, like a box. And these rectangles represent our features right now. So you can see that they are in different ranges. As we have seen initially, some of them are from 0 to 360. Some of them are around 0 point something. So their different sizes represent their different ranges. And if we're trying to fit them in a box by repeatedly trying stuff, is the equivalent of saying, okay, you should probably go be lower, and you should probably get bigger, and you should totally get lower, and then you should probably get bigger, and you should probably get lower. But now that I've seen that this is not filling the entire space, maybe you should get even lower, and you should get even bigger. And that's what basically the whole weight assignation that's happening behind is doing. And this box is our target. But if instead, from the get-go, we started with some features that look more like this, so scaled, we remove the mean and divide by the standard deviation, we change basically how big the range they can vary in is, we'll most probably need less iterations in order to make them fit in the box, because it's going to be something like, oh, okay, I'm sorry, I changed the color here, but you're going to get a little bit bigger, and you're going to get a little bit lower, and then you're going to get a little bit bigger, and ta-da, we just made this fit way quick, clear. But you don't need to trust me on that. We'll just look at this happening. So what is going on here is we're basically saying select all the input columns, make them go through a standard scaler, which does this to them, which is a pre-processing step. And we're creating this pipeline that says first pre-process the data and then apply the logistic regression that has the random seed and the class weights balanced. So what's basically happening here is we're saying use a standard scaler on all of our columns. So let's execute this. And then this new pipeline is our model that has an embedded preprocessor in it. And then what we're doing is we're fitting it on the trained data, then predicting on using the dev data, and then evaluating it. And we can see that our results seem to be the same. So this little step did not help with getting better results. But if we look at the number of iterations it took us to get to this same results, we can see that we now performed 13 steps instead of 43. In this case of a small data set with few examples and few features, which are our columns, maybe this is not such a performance issue because we've seen that it took less than a second probably in both cases. But in cases of big data sets, these things matter. And sometimes they can also help with the performance. In the next following cells, what we will see is we'll be getting a comprehensive look at the data. This is a function that I wrote. It doesn't really matter what happens behind, but it basically will give you a view of what we've predicted correctly and what not. You have the code to get the same kind of plot. And what we're seeing here is with blue, we see the true negatives. So all these blue were coronal mass ejections that were not geo-effective that we've correctly identified as being so. And we're going to make them disappear. And now I'm sorry if you cannot see the yellow so well, but the yellow ones are false positives. And we've already seen that we are predicting quite some. But if we hover over them, we can see some of their initial features and get a better understanding of our data. And we can see that this little pattern that's going on here seems to be events that have the central position angle and angular width equal to 360. And we have with green, with green, we have our true positives, which is the coronal mass ejections that we've correctly identified as being geo-effective, and the 3 red ones that we have missed. And what we're seeing after that is the values of W and B that we have, that the machine actually has computed in the background. And this was it with the logistic regression, and we're going to move forward to the feed-forward artificial neural networks. But before that, I would like to know whether there are any questions. All right, moving on. The simplest way you can look or visually imagine a neural network is something like this. You have a number of inputs in the input layer, which is your input features, or the X, and you have an output layer, which in our case only has one neuron, one single cell, because we only have one output, which is Y, 0 or 1. And in between, we have at least one hidden layer, which is an intermediary layer with a number of neurons, in this case 4. But obviously, you can have many other hidden layers with various number of neurons. And the bad news is getting the correct or the optimal number of hidden layers and neurons is as much of a science as it is an art. So basically, there's no mathematical formula or way of knowing exactly how many hidden layers or hidden neurons you should have. And this is part of your work as a data scientist or machine learning practitioner to try different configurations. And what I usually do is start small and gradually add more neurons or more layers in case I need better results, and see if doing this actually gives me better results. Because as we've already seen, or as I've already told you, you might not need a complex neural network for your task. You maybe can do with a few neurons or no neurons at all, meaning a simpler model. And what happens in each and every of those neurons is actually very similar to what we've seen for the logistic regression so far. There's basically in each neuron a sum being made, exactly like in the logistic regression. Each of the inputs is multiplied by a weight and then summed, and there's a bias added after that. So far, this is very similar to the F we've seen above. The difference is that this happens in every single neuron and in more advanced hidden layers. So the input is not the original input or the feature, the initial feature. It's not central position or angular width. It's actually the output of the neurons in the previous layer. And then there's one more difference because we want something more complex than just the linear function that we've seen just simply added a number of times. We want to add some non-linearity, which happens by feeding this output in a new function that's called an activation function. And after we're getting this result through this activation function, we actually get the output of every neuron. So what's going on to what's going out of it and through the other neurons and in the following layers. And there's some activation functions that are well established and more commonly used. And these are some of them, if not most of them. And in our case, you can see their shapes here. And in our case, since we want to predict a 0 or a 1, we can see that the sigmoid could be a good choice for this final neuron because it gives results in the 0 and 1 range. So this is what we're choosing for the last neuron. In between, you can experiment with different activation functions, and this is part of the fun. Do artificial neural networks make sense so far? The principle is the same. The information is going to go through all of the neurons, all of the layers. We're going to get the prediction, see how far from the real value we are, and then update each and every or some of the weights by going back and seeing where we could adjust something. And then we're moving on with another sample that's going to the newly computed or newly adjusted weights. And we're trying again and seeing what prediction we got, seeing how we can improve those weights, and doing it all again. Does this make sense?
I have another question just so I can understand and would be able to actually code this up from scratch myself.
All right, yes, please.
So if you go to the what's going on inside a neuron panel,
That's right.
Then that first step, X1 with W2 to produce a sigma, is a linear transformation, or it's actually a dot product. And
it is.
These are the X's are the raw data going in, and the W's are a kind of weight.
Yes.
And are those W's positive definite?
No.
Okay, fair enough. And then you add the B to it to derive a new quantity called sigma. Okay, I understand that bit. That's all linear mathematics so far.
That's right. That's right.
And then you have this activation function, which if
That's
it's like
right.
some of the activation functions below, is a continuous function of the sigma on the x-axis. But
That is correct.
it has to be a nonlinear thing, because you must have a critical point at which you say, well, if sigma is bigger than, say, 3 or smaller than -3, then you set it to 1. And if it's smaller than that, you set it to 0. Is that what happens? And is that what the nonlinear component is?
Not quite.
Okay.
Up until the
'Cause
non-linear point, it's all completely fine, except that these are not, the x's are not only the inputs. The x's are our original inputs for the first hidden layer, but then in the
Yes.
second hidden layer, the x's are actually the outputs of the neurons in the layer
Okay.
below,
Yeah.
behind.
Right.
All right, so then we're adding some non-linearity. The
Yeah.
reason we're doing so is because we want a more complex function. We want something that is not linear. And that's how we're telling the network or the machine to look for complex functions, like in the sense of complicated functions that we might not even understand or we wouldn't be able to find ourselves. But it is simply for introducing nonlinearity from my understanding, and the way we're bounding this result, or the way we're making it say whether it's a 0 or a 1, is actually another step that we're going to do soon, because in fact we could use 0.5, let's say, as an indicator that what is below is more similar to 0 and what is greater than 0.5 is more similar to 1, and then assign these binary values. But we could well enough use another threshold. The reason that we've chosen the sigmoid function is because we want our output to already be in this range. We don't want to normalize it again, although we could if we used another function and then tried to assign ourselves some breakpoint, I think that's the notion, or I'm sorry if that's not the exact wording you've used. But yes, we should define one ourselves. But we could use. Does this make sense?
I was more interested just in the above, in the what's going on inside a neuron thing, as understanding what you want to have out of this activation function that then goes to the right. And I think you explained it very well. So thank you.
All right, thank you. So what we want is non-linearity. We want to add something complicated, let's say, to other than simple linear functions that go on through a network. So let's move on to this, to working with artificial neural networks. And we're now switching the libraries we're using. We've used scikit-learn so far, and we're going to use Keras and TensorFlow for now on, but that's not necessarily important. The reason I'm saying this is because we no longer have a function that takes as a parameter this class weight equals balanced. We will simply need to use weights as an input parameter, and we're going to say assign this balanced weights. But this is the only difference, the way we're telling it to do it. The weights are still balanced and the principle is the exact same. So we're going to go quickly through that by executing this. And this other cell right here that says normalization is a scaling layer. So scaling pre-step, as we did with standard scaling before. It is just another way of limiting the range in which the values are varying in order to speed up our computations, as we've seen. So we're just going to execute the cell as well. In this next bigger cell, what we're saying is we're creating the neural network. And what we're saying basically here is create a sequence of these layers. And in the first one, we say, this is the input layer, take the inputs. Then we say normalize them with this normalization pre-processing layer that we've created here. So take the inputs through the normalizer before you're submitting them to the following layers. And this is our first hidden layer and only. As you can see, if we wanted to add more, we would just copy this line and paste it below a couple of times, as many as you want, and just specify different number of neurons if you wanted them to have different number of neurons. The number of neurons that you see here we will specify as an input to the creation of our model. When we call create model, we'll specify how many neurons we want to have. So this is our hidden layer with a number of neurons. We're using rectified linear unit, or ReLU, as our activation function, which is this one right here. And this is our output layer, the last one, which only has one output. And as I've said, we're going to use the sigmoid activation function. What we're adding here. Yes.
In the previous part of the code, the normalization function is used is from which library actually?
This part is from Clara's pre-processing.
Okay, so one doesn't have to mention that it is like Keras dot normalization, something like that.
I have imported this at the beginning of our presentation. I did not know you'd be interested in this. I'm happy you are. Basically, there's this cell that imports all the necessary things. And if we look for normalization, we can see TensorFlow.keras layers experimental pre-processing import normalization.
Okay.
So everything we're using is right here at the beginning of our notebook.
Yes.
It is imported there. Moving on. This line right here is basically telling us how we're computing the error or how we're basically computing the difference between the predicted value and the expected value. I can show you the mathematical expression of this. It's basically just a way of computing the difference in a more complex and meaningful way rather than just saying expected value minus predicted value or vice versa. And this is with the creation of our model. And here we have some hyperparameters. And the name hyperparameters refers to parameters that we are not learning, or the machine is not learning, cannot discover itself, but that we have to feed. Whatever the machine can learn is called a parameter, and what we have to submit is a hyperparameter or a parameter related to learning, the learning process. And now we're just going to specify some intuitive values. We're just going to try and experiment with them and then see how we can get better results. And so we're saying, let's use a single neuron in our single hidden layer. Let's use a learning rate of 0.0001. And the learning rate refers to how big the changes in weights are going to be when we go back to our network and try to get better weights, optimize them. So this value usually ranges in 0 to 1. And the closer it is to 1, the bigger the changes there are. So let's say you have a weight equal to 200, and when you're going back, your machine thinks that it should be slightly lower. If you have a learning rate of 0.99, it could go down like, let's say 150 units. So you would get 50 out of that weight. But if you're going 0.001, if your learning rate is 0.001, it means that you will make maybe a safer assumption. You'll change this value just a tad bit. So maybe you get 190 instead of the original 200. But this will most probably reflect in the time it needs, your neural network needs to train, because it's making smaller changes. We'll see that in a couple of seconds. The batch size means the number of samples that you consider before making a change. So while you probably, or I have made you probably think that each new sample makes the machine change the weights, you could give that input to the batch size of 1, and it would basically make a change each time you feed it a new sample, so a new row of X values. Or you could use a bigger portion of your data. So it would look at, let's say, in our case, 32 samples before it decides what change to make. You could also look at your entire data, but in the case of huge data sets, this might be impossibly long. So this batch size refers to the number of samples that it looks at before making a change. And the number of epochs means the number of times it goes through the entire data set until it stops and gives you, stops training, basically. So the amount of times it goes through all of the data, meaning the number of batches that you need to go through all of the data. Do these hyperparameters make sense? I will take it as a yes. And what we're doing here is basically writing some configurations that you do not really care about. It's just for a plot that we will see soon. Here we create our model and we give it this input shape that you do not really care about, that I have configured here for you. And then we're basically saying, take this number of neurons, 1, and
Andrea, can you unmute? There you
yes,
go.
I'm sorry.
No, you're good now.
All right. Can you see my screen?
Yes.
All right. I'm not sure where exactly you lost me.
About 2 minutes ago, maybe less.
Oh, okay. That's a lot.
I believe you were explaining that you are now trying to create the model, and you were saying what you need in order to create the model.
All right. So did you hear the entire, what are these hyperparameters talk?
Yes.
All right. So these are the configurations. I was saying these are configurations for a plot. You do not need to worry about them. We are creating the model here. We're giving it this input shape that you do not care about. We're submitting the number of neurons, which is 1, and this learning rate that we're specified. And we're going to train our model the exact same way we did with the logistic regression by using the word fit on our trained data set, these examples and these outputs, and we'll have to submit the batch size that we've specified here, the number of epochs that we want to train over, the sample weights, which are, I was telling you, training parameters. So we're telling the machine use balanced weights. This is simply about how much it should spit out and show us. This basically says where we should and how it should handle the logs and the plotting. And what we're using here is 20% of our data, of the training data, very similar to how we've separated the development set. We'll be using this percent of our data for validation, basically, in this fit. So we have a double look at the way the model is performing. So the way it's performing on the train data, which is data it's seeing, and the way it's performing on data that is not seeing, that it's set apart for validation. Let's create and fit our model. Apparently I have not executed these things before. If there's something similar happening to you, you just need to execute these cells before that you might have missed, and then try again. And it is working now. It's basically training, and after that, we'll just look at how well it's doing. And what we're going to see is actually is called a learning curve. And what it's basically showing us is the way our error hopefully decreases. Let's look at it. So what we should see basically is something that is going down, hopefully, because this means that we're learning something, that the error goes smaller and smaller. It is taking its time. And so what we see here are two learning curves. The orange one is for training. We can see that in its name. And the second one is for the validation set, so unseen data. And we can see it performs very similar. That is good. That is what we want, for it to perform as good as it performs on the training set, as it on the data that it's never seen. We can see that the error is in fact going down, but we can see that right here it's taking a while before it's actually going down. It could go even more abruptly, meaning faster. And I would like to show you this ideal learning curve, which basically shows us a constant decrease of our error. So the error is getting smaller and smaller, which means the model is learning better and better how to perform on our data. And usually, if you've specified more epochs than it's needed, the loss or the error is going to go something like this, like a line, because it simply means that it cannot perform better with these parameters and this architecture. It means that it's as best as it can go. The error doesn't go any lower than that. So maybe
Andreea, I'm sorry to interrupt you.
Yes, please.
We have a comment. Running this cell just yields a Google side error, no explicit error message. Does anyone else have the same problem?
Running this cell just yields a Google side error note.
Works for Lindsay. Works
All
for
right.
Alex.
So yeah, I'm having that, and it's just like a Google picture 403 that's in there. That's all we know. That's all I'm getting running this cell.
Running which cell exactly?
The TensorBoard log direction logs fit. Yeah.
Okay. Can you try again?
Yeah, I did, and then it just came like reusing TensorBoard on port 6006. Started.
Okay.
Yeah.
Okay, yeah, it should start maybe.
But it's still the same error.
Can you, there's on the left side of the screen, there's something that looks like a folder icon.
Mm-hmm.
Can you open it and see if you have a folder that says logs?
Yes, there is one.
All right, and if you open it, you have fit and then some other folder. Yeah.
Yeah.
All right.
I have three folders in there.
Inside
like
the fit.
N1, yeah, inside the fit, like N1.
All right, so
and
you
then
probably
some numbers.
Basically, you might have executed this line more times. So you have the logs there. Basically, the error is just at plotting them, which is from the TensorBoard side. Are you sure you have executed these lines before at the beginning? Most probably if you've executed all of them, but can you see if there is like a number close inside on the left side of the cells? That basically means that they've executed. And if not, you should load those.
Which cells? Like the
Right at the
ones just before? Ah, right at the beginning.
Right
Okay.
at the beginning, yeah.
They seem all to have executed.
All right. And I'm not sure. Maybe you could copy this lines that initialized actually this line right here, but it shouldn't necessarily change anything, but maybe just
Okay.
could you run this again, please? And then this again.
Yeah,
this
yeah. Otherwise I can try myself a little more. Then I'm not interrupting too long.
There will be another step that involves this TensorBoard. I will try to help you because we'll have a hands-on little exercise and I can try and see what's going on there. Otherwise, you can just look at my plot and
sure,
understand the bigger picture. I'm sorry it's not working for you.
No worries.
And Andrea, we also have a couple comments in chat from Amy.
Yeah. All right, it doesn't change anything. Mine also showed an error in the beginning and worked afterwards. Okay, so maybe running the cell again could help. And Amy, yes, if you're seeing two plots, you can look at the names here. And what this basically is saying is the number of neurons you've used, the learning rate, the batch size, the number of epochs, and then you have a timestamp. And if these are different, it basically means that yes, you've ran the same configuration multiple times at different points in time with different timestamps. If we have one for training and that one for validation, that is perfectly fine. There are two here as well. They're just one covering the other. But yeah, it's no problem if you've executed the cell above multiple times. It doesn't change anything. You just have two plots. That's right. Thank you, Aline. So what I was saying is that maybe we could make this line, this error go lower faster. And if you remember what I was saying at the beginning, maybe this could, increasing the learning rate, so increasing the weight change, the amount of change, I guess, we apply to the weights each time we iterate over our data could make this go lower even faster. So let's try with the value of 0.1. So you need to modify in the cell that says set initial hyperparameters. You need to change this to 0.1, execute the cell again, then execute the cell below with the creation of the model and the fitting again. Wait for it to train. And then when we will look again at the TensorBoard, we will have a new set of learning curves, and we can see whether learning faster yields better results and gives us a more ideally looking learning curve. Mine has trained already, so I'm going to look at TensorBoard again. Hopefully it will want to work. It's sure taking its time. And so what we see here is that the error is certainly lower. By clicking on these checkboxes, we can choose what we want to see and what not. So let's not look at the initial model. And let's not use any smoothing. So what we see here is that it basically starts off with an error, and then since the changes are so big, it cannot find a point to converge to. It doesn't yield an optimal result, but it actually fluctuates. You can see that the error is also growing, so increasing, and that is because the changes are so big. So maybe trying with smaller learning rate could help, or maybe stopping after a smaller number of iterations could help. Like, for example, before it starts to increase. And maybe this could lead to better results. What we're going to do now is plot our predictions right now that we have with this current model. And here we have our original dev set with the original labels. And what we see here is something that is colored gradually. And this happens because, as I hope you remember, our output is based on a sigmoid function. So we are getting a value that is in between 0 and 1, but we do not have a threshold set yet. So it's basically a continuous result. But we can see that if we look here where we have some geo-effective events in the original set, that it is more similar to, it gives results that are more similar to 1. And it predicts them as being closer to 1, all of this. Let's see what results we would get if we would set the threshold at 0.5. So what we're saying here is, with this, is that everything that's above 0.5 is going to be considered a 1, and everything that is below is going to be considered a 0. And if we run this, we see that our accuracy is worse than what we have previously with the logistic regression, and that we have this recall value, which is better, but also a lower precision. We could try with changing the threshold. Maybe another threshold could yield better results. And apparently 0.9 is too high. It doesn't identify any of the geo-effective storms. Maybe 0.6 or 0.8 could be another good value for a threshold. But this is just to show you that the threshold that you set could influence your results. In the following minutes, we will still be using 0.5 as the official threshold as it is commonly used. But what you will be doing is try and find the best hyperparameters for the network. And you won't be doing so by simply changing the result, the input here, because this would be tedious to try so many configurations. Instead, you'll be using an already implemented function called grid search. And what you will do is basically supply some hyperparameters that you want to try out, and it will automatically try all the combinations. I will go through the details of what you need to do in a few seconds. What I want to tell you before is a detail that is used in this grid search, but that is also an important concept for machine learning. So far what we did was train on a set and then test our results on another subsection of the initial set. But let's go back to the good teacher. And let's say that this time we want to see how good of a teacher they are. And for that, we will pick a student from the classroom that they're teaching and use them as the representation and the evaluation metric, let's say, for how good of a teacher they are, because this is what we've been doing. We've been choosing one sample and based on our results on that. But if we do so, if we choose just one student out of a classroom, we might have the bad luck of choosing the laziest one, let's say, who just doesn't want to study. And so their grades are not a reflection of how good the teacher is. But just the same way, we could also pick the genius of the class who simply knows everything from kindergarten. And therefore, it wouldn't be the input of the teacher. Their performance wouldn't be an accurate reflection of the teacher's value, let's say, or performance. But what a more accurate way of seeing how good the teacher is by looking at the mean of the performances of each and every student in their class. Right? This would give a both less optimistic and less pessimistic view of their performance. And this is the principle behind k-fold cross-validation. It's basically saying split the data that you have, the data set, in k-folds, in k-subsets, and then train on k-1 out of them, and then test on the other, and do this until you have tested on each and every subset of your data. And then the mean of your performance would be a more accurate and more realistic way of expressing your performance on this particular data set. So you're basically reusing the same data, but you're always hiding or setting aside some data to test on, and therefore you're testing on all of the data at some point. This is one principle that is used in grid search. Basically, you will perform a search on a number of combinations of features to find the best one, according to what you specify, of course, but it won't do so by simply iterating through the data once or like using just a part of your data, but it will go through all of it and test and train on all of it, so it will give you a more accurate performance evaluation. And this is where you will have to introduce the hyperparameters that you want to try in this form. So basically, you can choose out of these parameters that we've tried: the neurons, the batch size, the number of epochs, and the learning rate. You need to write their names between apostrophes like this, let's say neurons. And the values that I want to try are 1 and 7. And I also want to experiment with the learning rate. You will have time to do this yourself. I'm just showing you how you need to do it. And I'm going to try these values right here. Feel free to try anything you want with the mention here that the learning rate should be in this range, that these are some common values for batch sizes, and that it will take some time to try all these combinations because we'll try each and every combination. So please do not use too many values at once if you want to see results quickly and maybe try other things then, because it will take some time. So try to limit yourself to 2 or 3 hyperparameters and 2 or 3 values. Of course, yeah, after you see that it tries them and you get some results, you can perform this grid search again. So what you will have to do here is write the combination of hyperparameters that you want to try. After that, we will define the model. You do not have to do anything or care about this other than comment or delete the parameters that you're trying here, because otherwise this will be using the default values that we've set before and you won't actually try these. So what you need to do is look at what you've selected here to try, like neurons, and either delete this row if you do not want to perform this again, or comment it by adding a hashtag before it. And when you want to use the number of neurons set before or want to try another hyperparameter, just delete this hashtag. And since I've also selected the learning rate, I'm just going to comment this again. Then you will have to perform this grid search. You just have to execute this, and then which is the configuration actually, and then the fit, and then look at the results. You'll get similar to this. It will show you that it's trying combinations, and then you will get something that it says best score and an evaluation, and then it will tell you which of the parameters that you've tried led to the best results. There's one more mention that I have to make here. I would have wanted to ask you what we should use to compare two models, but since we're running out of time and I want you to do this hands-on material and maybe ask some questions and see what happens after, I will give you the result, the answer from the get-go. Basically, we need to compare two models, and we've already seen that comparing their accuracies would not be the best idea because the accuracy might be misleading in our case. So since we care about both the recall, so the number of true positives, the number of correctly identified geoeffective events, and the precision, which is the reflects in the number of false positives, we will use a metric that takes both into account. And its formula is right here. So it basically takes both precision and recall into account. And this is the reason we are using this. What you do here, what you need to do now is basically select some hyperparameters, run all the cells below until is this actually okay? And see what you get. Of course, if you want, you can go even further and then set your hyperparameters here. Do the same thing that we did before, which is basically create a neural network, fit it on the hyperparameters that you've set, that you've received as best results, and then look at the learning curves and see if they look anything close to the ideal ones. I will give you, let's say, 8 minutes, hopefully, to do this. I hope you manage to try stuff so that we can discuss some results after. Does anyone know and understand what you have to do?
If there are no responses, I want to acknowledge Andreea for her remarkable teaching skills and how complete this example really is. I'm extremely impressed, and I want to congratulate you on doing such a fine job. And unless we don't, in case we don't talk again in the near future, I wish you all the very best.
Thank you.
I hope you consider going into this kind of system science, the science part, as opposed to technology in commerce or something, because I think you'd be a very valuable addition to our school of young scientists that are currently coming through. So congratulations. I think that was
Thank you.
a
Thank you very
fantastic
much.
presentation.
It looks like we do have a few people in chat who are running it right now.
That's great. Thank you. Both for trying stuff and for providing feedback. I will be trying stuff myself.
So Andreea, if I can take just a moment to ask you questions that I'm interested in.
Sure.
When you go through this business and you've convinced yourself that you have something useful, basically what you have is a validation purely through statistics. Is that right?
That is correct.
So at the end of the day, you end up with predicting the smallest number of false positives with a machine that's you've had to help get to the solution with various tests and what have you. Now, I guess the interesting part for me, because I'm a physicist, not a machine person at all, is how I wonder what you would need to add to your list of input parameters to improve these results. And I don't think it's not the responsibility of the algorithms to do this. It's the responsibility of the scientists to pick a better set of observables that might contain more information, right?
That is correct, yes.
Okay, so is this something that interests you personally? I mean, is this, or are you more interested in the performance of algorithms no matter what the problem is, or is it a mixture of both?
It's most certainly a mixture of both, and I think it has to be, because as I was saying, the performance of the machine is as good as the data we feed to it. So you, as the data scientist or machine learning practitioner, you should be interested in the data you're giving to your model and what you can do about it. This is actually something that I've hoped we could cover, but unfortunately, due to time restrictions, we won't be able to. This is called feature engineering, and this is the next thing after trying hyperparameters that you can try to do in order to improve the performances of your model. And what we would have been doing is try to add some features that are basically simply derived from the ones that we already have, which is to add polynomial features as a combination of each feature with any other, each other feature. So 2 out of 2. I sorry if this is not the correct English expression of this, and also each value to the power of 2, which basically gives us a bigger data set. We could also obviously search for other unique values, and maybe the face of the sun or the direction of the CME could help in improving our precision, because at the moment we're not taking this into consideration, and it could be valuable information that we're missing and that obviously the machine is missing. So to answer your question in less words, the part that's regarding the data is at least equally interesting.
Yeah. So in this particular problem, as a solar person, I know that the problem of this kind of prediction is that sometimes the trajectories of CMEs can change as they start at the Earth, the sun, and move to the Earth. The natural, so I mean, my answer to my own question would be, if we added data from a spacecraft that was not going around the Earth but looking sideways, that is the kind of thing that I think probably would improve the statistics here. And so this gets to the point of knowing what is the information content of your data. And that is something that normally can be assessed only through, if you have linear relationships between the data that you're looking at and the thing you really want to know. And that is not the case often here. So this is really a skill. And the reason I bring it up is because it's at the heart of this meeting with people with skills like you've developed in this problem. if you were then to go on and develop your skills in the physics part of the sun, you would be in an incredibly strong position to do very impactful research, because you get a feeling for what kind of data are missing that you need to have in order to solve the questions you're trying to ask. And this is something I think we want to talk about later in the meeting, hopefully on Thursday, if I'm making sense to you. So I think the idea of joining with a team at this stage would probably benefit a lot of people in a team to have someone like you on board that's already been through this kind of thing, so that they might be able to prepare a nice set of a more complete set, a more informational set, information-rich set of data at the beginning, and then the algorithm will take care of the rest. That's sort of the point of this whole meeting, actually. So again, you kind of hit the nail on the head here, I think, with this wonderful demonstration.
Thank you. Thank you for your words. I'm sorry to interrupt you if that is the case. I was wondering if anyone has any other questions. I've also ran my grid search and I've got these results. I'm going to look at them right now, because the point is that even if these results look super good or like better than mine, like you're getting a score that is better than mine, you should look at your learning curve and see that your error is not actually increasing. And besides that, the error on the validation set, which is the unseen data, is not increasing. Because that will show that your model is not generalizing well, that it's only performing well on the data that it has already seen, and not on data that it hasn't. Is there anyone who would like to share their findings and their best neural network architecture, let's say, the best hyperparameters? I think Aline has shared his, and his score is actually better than mine, and it looks good. He basically has a different learning rate, and if his learning curves look good, kind of like this, then his model is probably better. And we've also seen, I can also see that Vanessa used some combination that yields better results. She's going to look at the curves and see if the model is not overfitting or underfitting, which are some terms I did not explain, I now realize. But basically, it would mean that the model is not performing well. This being said, if there's no one else who wants to share their findings, there was some other part in which I would have showed you how to try some feature engineering, add some new features, and how to cross-validate your entire set. So no longer use just the dev set and the training set separately, but use the entire train dev set with cross-validation to see if your results are as good with cross-validation as they were in the dev set. And then we would have looked at the train and test set, and we would have asked ourselves whether the values are similar between training and testing, and whether this is good or bad. And I'm going to give you the answer now, which is the values of these metrics should be similar or very close one to another between the train and the test, both in cross-validation and in when testing on a different set, because this shows that your model is not only learning to reproduce data, that it's not only performing well at training, but that it's understanding the essence of the data, that it can generalize well, that it can extrapolate from the data it has trained on and perform just as good on a test set. And after that, we would have chosen the best model and then tested on the data that we've set apart. And to conclude, what I hope you have learned from this meeting and that you're going away with is that in order to have a complete machine learning project, we need to pre-process and analyze our data, try some different algorithms, test, improve, and then do this all over again. I hope you have seen that scaling our data, cleaning our data is a very important step in machine learning, or an important pre-step. I hope you've seen and understood how we test our data, and I hope you've seen some interesting and perhaps useful tools that you can use for your own projects. This being said, if there are any other questions, I would be happy to answer them now. If not, you have my email address right here if you maybe remember that there's something that you didn't manage to ask. And you also have links to everything that we've used. And what is left for me to say is thank you for your attention. But if there are any other questions, now is the time to ask them.
That's a nice talk, Andrea. Thank you. Just was curious about one thing.
Yes.
When you have data which is like this biased with very few positive cases, there's something I have heard in another talk about resampling. Would you like to comment on that?
That is right. If you go back in the poster gallery, you can see that I'm also talking about this particular issue in my poster. And indeed, another thing that you can try besides using balanced weights is either removing some of the samples from the majority class and then creating a balance by simply removing some data. But since you'd be losing some information that you might not want to lose, or not that much, because we have extreme imbalance here, there's also a technique called oversampling, in which you can either actually not kind of, just simply copy samples that you have in the training set and just add them. But maybe you don't want to introduce the same information. But this would be rather similar to the class weights, the balanced class weight. And there's also another technique called SMOTE, which means synthetically minority oversampling technique. And what it basically does is it looks at the minority in your data set and it tries to create new data based on a group of similar samples. So it sees what looks similar in the minority sample and it creates new data from that. And you can try and train on that data, but you should set aside a set of original data or data from the original test set and see if your model that you're training on the artificially created set is performing good enough on original data. I hope this answered your question.
Yes, thank you.
If there are no other questions, Catherine, I think I can give the floor to you.
Very good. Yes. Thank you, everybody, for joining us today. I believe a survey will be sent out for the session after the symposium. You have Andrea's email. So obviously reach out to her with any questions. And obviously we are here at CPAESS to help you with anything you need throughout the symposium. Phil, do you have any final comments? All right. Well, thank you so much for joining, everybody. Have a great rest of your day.
Thank you. You too.
Thank
you so much for joining my session.
Hey, Phil, is there anything else I can help you with?
Let's see, where am I? Sorry, no, I collapsed my file. Thank you so much for your work. It really helped at the beginning and made us, I'm sure it made Andreea more comfortable. I thought it went very well, and I really appreciate your help.
Of course, we get some great feedback. I think it was an excellent session.
Yeah, good. As I said, you know, what can I say? I mean, you know, I feel like a fraud in this area after 30 years of researching, and you have quality people like that. So it's really, really impressive. If we could get her to come to NCAR, I would.
That'd be nice.
Okay.
All right,
Thank you
well,
so
have a
much.
great rest of your day.
Nice
Thank you
session.
so much.
Yeah. Yeah. Nice to meet you online. Thanks. Bye-bye.
Nice to meet you as well.